Welcome to CO2 Monday in the Refrigeration Mentor podcast. I'm your host, Trevor Matthews, and I want to thank everyone for taking the time to come and watch these videos and listen to a little bit about CO2. We've been doing this for a long time, have some amazing guests on, and I got a returning guest this week, Patrick Clardy from Danfoss. This guy has so much CO2 knowledge. I have to keep bugging him to come back on because it's enjoyable to talk with people who are super passionate about CO2 and refrigeration. This week, we're going to be diving into, again, we're going to go over ejectors, diving into what ejectors are all about. And then we're going to be diving into their CALM system. Really, this liquid ejector as well. It's actually a system, a full system that really can make your CO2 system more efficient. I want to hear more about it. I've been learning a little bit about it, and I'm excited for the conversation today. Patrick, welcome to CO2 Mondays again. How you doing?
Thank you for having me again, Trevor. Doing good?
Yeah, that's awesome. We seen each other the last time we were making some videos at Chilventa in October, and now we're here again talking more CO2. And really, because I love your passion about refrigeration and sharing your knowledge with me, and I really appreciate all the knowledge you've shared with me and the audience so far.
Yeah, it's great to be here, and it's your enthusiasm is it's very exciting. So yeah, keep it up. Absolutely.
Yeah, that's it. That's what it's all about. It's all about helping others get to the next level in their CO2 knowledge. So we're going to dive in first. We're going to review ejectors. We talked about it last time. So if you want to go check that last video out, I can't remember the podcast number, but or the YouTube video, go and check on the CO2 playlist. It'll be there. I got a lot of views already, but we dove into the high pressure and low pressure ejectors, and we want to review that again because this is something that's still new, not new to the industry, but it's still new to a lot of people. And it's good to continue to put the reps in, learn about this stuff over and over again. That's how you get better at stuff.
Yeah, absolutely, and especially when it comes to ejectors, that is, let's say, CO2 can be challenging for some people, especially when you're new to it. And then CO2, the ejectors, that's the next step, right? That's so just when you think you know everything about CO2, ejectors come in, and you have to start all over again because
Yeah.
it can be tricky, right? And it's not so straightforward as it might look. It's not just another valve or not just another product. You need to take care, and you need to know when to use it, how to use it, and especially when not to use it.
Yeah.
So. Yeah, but we can go over some of the ejectors, and I think because people hear so much on ejectors, you hear so many different terms. You hear low pressure ejector, high pressure ejector, liquid ejector, and sometimes you simply you're lost, right? You lose track. So we can go over that, and just the high pressure and low pressure we touched on a little bit longer during the last talk. So, but I'll give a short recap, and then we can dive into the liquid ejector a little bit deeper, let's say.
Yeah. I
That's
love
all
it.
right with you.
Yeah, no, that sounds perfect.
Right.
Once again, this is how I learn is just continue to talk about the same things and little bit of knowledge. It's all about the small simple steps. A little bit of knowledge here, there over time is a lot of knowledge, right?
Right. Yeah. Correct. So let me start by sharing my screen. Hope you can all see it.
Yeah, perfect.
And I love this picture, by the way, just in between, because this really shows where we have started in the 1800s with natural refrigerants, and we went astray from the path for a short time, and now we're basically back where we started in natural refrigerants. So that's basically back where we all started 200 years ago or so.
That's crazy. You know what I mean? When we talk about CO2, people are, CO2 is it's new, but that's 1834 that people started using natural refrigerants. So it's
You probably know, but the Titanic had a CO2 system on board, so it's not so new.
yeah, and that's what I love when I talk to people about it. It's like, oh wow, I did not know it was CO2 has been around that long, but it has been, and this is something that we should be sharing with people because it's not a new refrigerant out there. We've been using it for a long time. It just went away for a little while.
Yeah, and a lot has happened since then. So
Yeah.
absolutely. So let's see. Let's dive in. If you have any questions, just shout out. Right. So let's just start with the low pressure ejector. And again, you have heard a lot of different terms, but in the end, there are just, let's say, three flavors. We got the low pressure, the high pressure, and the liquid ejector. And I hope after this session, it will be clear when you use which one. So the low pressure ejector, that is designed for usage in smaller systems. So you cannot use this for a large supermarket. There you would tend to use the high pressure ejector. And because in the end, they both look quite similar, right? They both are a large aluminum block with some solenoids on top, as you can see on the top left here in the screen. But the inside is quite different, and the geometry of the ejectors that are inside are simply designed different from each other. And the low pressure ejector, and we will go through the picture on the screen in just a minute, but it is designed basically to take the load from the whole empty system. So all the gas coming out of the empty evaporators, it's the point that's all going into the liquid ejector. So basically, when we looking at the top of the picture here, we have the discharge line after the gas cooler going into the ejector. That's the red line you see on the top. And at the bottom, we have the yellow line coming out, going into the receiver, where liquid and vapor are separated from one another. And then we have the middle port on the ejector here, where we see the blue line coming from the bottom part here from the empty ejectors, not going straight through into the empty compressors, but taking a left turn here, going up and going into the middle port on the ejector. And like I said, if you have a smaller system, and we're talking maybe 40 to 80 kilowatts, maybe 100 kilowatt max, that load can totally be taken by this ejector. So basically, it acts more or less like a compressor, taking in the suction gas from the empty evaporators. That means that the empty evaporators can run at a higher pressure, because the empty evaporators are basically only there to keep this liquid receiver on the set point it needs to be, which is, let's say, around 40 bars or so. So where those MT compressors would normally run at maybe, let's say, in Celsius -8 or so, now they can run 0, +3, +5. So instead of running at 28 bar, they can now run close to 40 bar. So basically, the MT compressors become somewhat of, let's say, parallel compressors running on the liquid receiver only. And that's the whole point of this LP ejector. And LP, low pressure, and that just means the pressure difference between the blue line, which is in the end the suction line, and the yellow line, the line coming out of the ejector going to the receiver. That pressure difference is, let's say, not too high in pressure. Let's say somewhere between 4 to 8 bars or something.
Okay, so I've seen this drawing, and everyone who've looked at low pressure ejectors seen this drawing. So anyone who's listening, you got the gas cooler, you got the low pressure ejector, and then all the other standard components, the flash gas bypass valve. So in this design, you do not have a high pressure valve. You're using the ejector as your high pressure valve.
Yeah, that's correct. And you can have it as an add-on if you want, because in the end, if the low pressure ejector runs into, maybe it's a bit too small, or you have more, you need more capacity than this ejector can offer, then you can still have a high pressure valve in parallel. So that one takes over once the low pressure ejector is running at full capacity, and then you can still start to open your high pressure valve if needed. But the ejector will always start first and last, let's say. But it's not needed, but you can have both if you want. Yes.
And then the way you save energy on this design, because these are 40 to 100 kilowatts, so that's 11 to 25 ton, we'll say, you save it by the suction lift. So you run it at a higher suction pressure to the system, so now you get a smaller compression ratio on your compressor, which you get more capacity, less power input on the system. That's correct.
Yeah, that's correct. Because in the end, you have heard about CO2 going into high ambient temperatures, where it was a problem of CO2 going into high ambient temperatures, and the problem was not the system. The problem was basically the empty compressors, because the empty compressors, they have the toughest life in the whole system. They have the highest suction pressure, they have the highest discharge pressure. So those are the ones that have use the most energy. So if there's one place to save energy, is the empty compressor. So basically everything we do when it comes to CO2 and high ambient has to do with these empty compressors. There we want to make their lives more easy, so to say. And that's what we do with the LP ejector, simply by raising the suction pressure on the empty compressor. So instead of running at, let's say, -8, we go to +5.
Yeah.
And that in itself is a huge step.
Yeah, for sure. And so these ejectors, I live in Canada, it's cold here all the time. This wouldn't be really a needed option, is that correct? Or is this for high ambient where it's like above? Yeah, so
correct. It makes no sense whatsoever. And of course it's a beautiful product, but it needs to make sense. And if you live in colder climates, because more or less talking about high ambient strategies, when you go from a standard booster system, normally the first logical step would be to have a parallel compressor in your system. And not even talking about ejectors. That's the next step over, right? So the first step you do would be, if you are in a somewhat warmer climate, maybe have an adiabatic gas cooler, or you have an intermediate compressor. And then if it really gets into the warmer climates, then we start thinking about ejectors. So it makes no sense in cold climates.
Yeah, thank you for pointing that out, because this is what's so important about CO2 is understanding the application, what your clients are looking for. Because people listen from all over the world here. Some people are in places where it's hot all the time consistently, and you need to know the right solution. So this is a viable option, but it depends on where you're at. And even in those locations, you got to justify, is this the right solution? Because there's other ones that Danfoss even has out there, so which is great. So, and then this one is only for smaller systems because the medium temp takes the whole load. Is that right? Because the medium temp compressors are now taking all the flash gas bypass and all the system load. Okay.
Yeah, and if you were to have a larger system, then simply the ejector is not able to take the full load anymore.
Yeah.
So take into account the LP ejector and the HP ejector that we will show right after. Those two ejectors are, let's say, high ambient strategies.
Yes.
LP for the smaller system, HP for the larger system, and the liquid ejector, that's not part of, let's say, the high ambient strategy. That's just to make your CO2 system more efficient, but has nothing to do with high ambient strategy.
And I love it, because we're gonna look at them soon. These liquid ejectors, but I bet you it looks the same as the low LP and the HP, or similar. Do they?
The block looks exactly the same. LP and HP ejectors, they both are a large aluminum block with say 6 ejectors inside, so 6 of the blue solenoids on top. The LE ejector, so the liquid ejector, that one is quite a bit smaller. So that comes in 1 or 2 solenoids. So that is smaller than the LP and HP.
And you said they're different, right? So they look the same. They got 6 solenoid, but inside, I guess they're designed differently to take more of capacity, I'm assuming, from the low to the high. because you wouldn't be able to take a low and put it in a high application. Internally, they're designed differently.
Yeah, there are under each solenoid is, let's say, one ejector. So we have 6 ejectors, small ejectors, standing upright under those solenoids, and they all have a different capacity. So typically, number 2 is twice as big as number 1, and again, number 3 is twice as big as number 2, and that's how we ramp up. So we start with number 1, then we cut out number 1 and open up number 2, and then we add number 1 again, and that's how we ramp up.
And so this would be all done through your controller. So the algorithm for, just say, this LP, it would be done, you'd put in some certain set points, I'm assuming, and then it'll be done through the controller. What are some of the things you've seen in the field that maybe the manufacturer of the equipment needed to understand, or the technician in the field supporting this? Is there 1 or 2 things, tips you could share that if they knew that before, it might have helped them out?
Yeah, well, knowing your set points and knowing your controls, that's key. And I know you mentioned this time and time again. And that is, in the end, you need to understand the controls, and we also have to learn there, because the controller that you see on the top right here, that's the AKPC 782B, AKPC standing for Added Cool Pack Controller. That controller has been on the market for quite some time, and it has been evolving since that time as well, because we are having regular software updates, because we also learn, right? We also make tweaks here and there to make the controller better. For instance, in the beginning, you were able to set the controller in such a way that the system went into what we call a gas loop. So that means you basically only have gas circulating through the top part of your system. So you have the discharge coming out of your compressors. You have gas coming back from your gas cooler going into your receiver, and the gas again is being pumped out by the empty compressors again. So you're just circulating gas, and you have no liquid anymore to go to your evaporators. And that's what we call a gas loop. And you were able to set the controller so it went into that state. And once it is in that state, it's quite difficult to get out of it. So now we have settings inside the controller preventing that. So even if you set some really strange settings, you will never go into that gas loop anymore. So we're also learning, and we're evolving, and together with the customers, of course.
I like that. I thought that's something new that you don't want to happen. You don't want to go into the gas loop, which makes sense, because now the compressors are running but not doing any real work in the system.
Yeah, you want as little gas coming out of your liquid receiver, because that part of the CO2 is not being used for anything. It just goes back in the compressors again.
Yeah, I love it.
So maybe if we step through the HP ejector, so that's we're now in a different picture. Notice the blue compressors, of course. The system now has.
You can throw a plug. You can throw a plug for Bach. That's all good. Not everybody knows it, but yeah.
I just want to slide it in, really sneaky. Looking at this system, it looks quite a bit more difficult, but in the end, it's not. It's basically the same picture. We still have the LT and the MT compressors. We have the gas cooler on top. We have an ejector on the top left, but it works a little bit differently. So where in a LP ejector, the ejector would take the full load from the empty evaporators, now it only takes part of that load. So if you look at the empty evaporators in just about in the middle of the picture, we have the suction line coming out, and then it's split. So we have one suction line going to the right, going into the empty compressors, and part of it is going to the left, going into the ejector. So basically, we are, let's say, reducing the amount of gas that's going to the empty compressors. In the end, the suction gas that's coming from the empty evaporators is going into the ejector. It ends up into the liquid receiver again, just as it was with the LP ejector. But now something else happens, because in the we now have the top line coming from the liquid receiver. It doesn't go directly into the empty compressor. So in this case, the empty compressors are not the ones keeping this liquid receiver on a certain pressure. It's the parallel compressors, or what we call the IT compressors, as in intermediate temp. Those are now the ones being directly connected to this liquid receiver. So where in, let's say, a standard booster system, your liquid receiver is connected directly to the empty compressors with what we call the bypass valve in between, controlling the pressure. But in the end, it makes no sense to have a receiver which is running on about, let's say, 40 bar, to be kept on pressure by compressors that are running on 28 or 29 bar. So now we have IT compressors. Those are the ones that are running on exactly the same pressure as the liquid receiver. And that is a must with this kind of system. So when we use an HP ejector, parallel compressors is a must. And that's also why an HP ejector simply cannot be used for smaller systems like we have with the LP, where you have maybe 40, 50, 60 kilowatts. It doesn't make sense for an HP ejector because you need a parallel compressor, you need empty compressors, and then the amount of compressors is simply too big for the capacity of the system. Doesn't make sense. So that's why HP ejectors, parallel compressors is a must. And there the saving comes in again. So where in a normal booster systems, your liquid receiver is being controlled by your empty compressors, now it's being controlled by the IT compressors, which are running on a way higher suction pressure. And again, the higher your suction pressure, the more savings you have, because 1 degree of saving is about 3 to 4% in your COP. So you can do the math there.
So I get this question a lot from technicians, and a lot of technicians that work on different CO2 systems, because you guys don't really manufacture the rack and equipment. You sell a lot of components to these rack manufacturers. They're like, I go to one system and it's running at, say, 40 bar. I go to another, it's running at 34 bar. Why are they all different? Can you kind of explain running the flash tank or the receiver at different pressures and how high pressure ejectors, and you just kind of explained it, right? You can lift up the flash tank or the suction pressure, but why do some manufacturers run at lower flash tank pressures, like say 34 bar compared to 40 bar?
I don't know if there's always a clear reason for this, to be honest. Typically 40 bar seems to be somewhat of a standard.
Which is 550 PSI for anyone who's around 550 PSI.
Yeah, thank you for converting that. It started out some years ago with somewhat lower pressures. Maybe we were in the 30 to 35 bar. Typically at the moment it seems to be around 40, but we see a trend going up. So we see a trend of higher liquid receivers, and we see systems running on 50 or 60 bar even. So the trend is up, and there's not always a clear reason for it. So
yeah, because I work with a lot of the technicians and contractors, and in a group, one contractor can say, yeah, the systems I work are running at 480 PSI, which is around 32 bar, 31, 32 bar. And then another person could be saying, it's running at 34 bar, which is like 515, 520. You know what I mean? So and they're just like, I'm not sure why. So it's something that you want to talk about with the OEM who designs that equipment and try to find the reason. Be curious. Ask the why.
Yeah. for sure.
Because the higher ones now that I see is that they're running air conditioning. So that's why they're running at 50 bar or 600 psi. Right.
Yeah, you need that. You could need that pressure for sure.
Yeah, I
So
love it.
we see a lot of changes. We see a lot of changes there. So is this so again HP Ejector, somewhat smaller, bigger systems, excuse me, and we're talking, let's say, 80 to close to 200 kilowatts, and which is more or less somewhat larger supermarket.
Yeah.
The ejector itself can do a maximum of around 200 kilowatts. So one ejector can do 200 kilowatts. If you need more, you can add another one, and you can have two in parallel. So if you need three to 400 kilowatts, if you have a somewhat larger system, you can use two, or you can use one and still have the high pressure valve on top. So when you need more capacity and you don't want to add a second ejector, you can use a high pressure valve, as you can see in the picture here on the top left. Just when the high pressure ejector is running at full capacity, then you can start opening up your high pressure valve to take the rest of the capacity, so to say.
Yeah. So if you have two ejectors, when you pipe them, do they have to be symmetrical? Like when you're piping them, or is there like specific piping design that you have to follow?
Well, that would make sense. Yeah,
Okay.
that at least because you need to make a split somewhere going into the two ports. It would make sense that they are more or less the same size, so they are divided equally. Yeah.
Would this bring any, because these are still high ambient in Canada? I don't even know if there's any of these types of injectors, or maybe, but like in colder climate, this is still for warm ambient solution. But would there be any advantage with this for like heat recovery or anything like that? Could you use these for in that sense?
That's probably the only reason why you would ever see an ejector in a colder climate. Yeah. So like we said, LP, HP, only high ambient. The only reason is when you have a CO2 system which is constantly running on a high pressure, for instance, on a heat pump or heat reclaim, as you say, because at least in Europe, it's quite standard that the supermarket refrigeration system also heats up the store. That's becoming more and more standard, and it is the standard on this side of the sea, at least. And so when you are running in heat reclaim, you are running on maybe forced on a higher pressure, and then even in colder climates, an ejector could make sense. But again, it doesn't make sense for colder climates as a general rule, so to say. But it could make sense when you're running on higher pressures. Always really think if an ejector would make sense in your system, and don't just mount one. There was a time when these ejectors were just coming up and everybody thought they were really interesting, and on every trade show you went, every rack you saw, there was an ejector, even if it made sense, yes or no. So people had the idea that an ejector, in what part of the world you are, it can optimize your system, and it's not true.
Yeah, good. Thank you for clarifying that. That's awesome.
Cool. Let's see on liquid ejectors. Let's see what's so different there. And looking at this picture again, it's not so dissimilar as you saw from the LP and HP ejector. In fact, this picture looks less busy than the one for the HP, but there is a big difference. First of all, again, the liquid ejector is not a high ambient strategy ejector, so you can also use this one in colder climates, because this is designed to optimize your CO2 system, whether it be in a colder climate or a warmer climate. It basically makes sense always. And I'll try to go through the picture with you. This is the liquid ejector is part of what we call the CALM system, and the CALM system is CO2 adaptive liquid management. And it's a large sentence, but it is, it's not one product, right? It's a system, it's management. So you need quite a lot of Danfoss components to make this work. So again, like we said, with anything with CO2, if we want to optimize anywhere, it's optimizing the empty compressors. And also with the liquid ejector, the purpose in the end is to optimize the empty compressors by running them on a higher suction pressure. That's the whole goal. So even if in 5 minutes you still get nothing of this picture, remember it's all about running on a higher suction pressure with the empty compressors. So in the end, what is causing, let's say, empty compressors to run at a certain suction pressure, right? We have typically those compressors, the empty compressors, are typically running at, let's say, -7, -8. But why, right? Probably the coldest object that we have connected to that system is a cold room running at +1, +2 degrees Celsius. So why do we have to run at a suction pressure of -8 or -7? And that's because we need the superheat in our evaporators. So basically, the superheat in our evaporators is causing the empty compressors to run at a relatively low pressure. So if we can remove this superheat in some way or form, that means that we can run with a higher suction pressure on the empty compressors and save money. Because again, higher pressure saves money, at least on the suction side. So now we have a system, and again, that's called the CALM system, where we basically run the empty evaporators at a lower superheat. And I'll come to how that exactly works in a second, but we can run the empty compressors with a lower superheat. But if we run with a superheat, let's say close to 0, that means we're not always running in, let's say, dry conditions. So we not always have dry gas coming out of the evaporators. We might get some liquid back. We might get some drops back. We might get some liquid back. That's part of the deal, basically. So, and that is the bright and shiny object you see in the middle of the picture, this traffic light, so to say. This is a suction accumulator. So this basically catches all the liquid coming out of this empty suction, catching it, and this vessel, and it's in the end this is a vessel, will start to fill with liquid. And the purpose of the liquid ejector is to remove the liquid coming out of that receiver, or suction accumulator, or separator, how you want to call it. Probably separator is a somewhat nicer word. So once this,
well, if we say separator, though, people are going to confuse every time you say separator, oil separator. You know what I mean? But you're right. You're separating the gas from the liquid, right? Because we do not want that liquid make it back to those compressors.
Correct. And this small vessel is only there to make sure this liquid doesn't reach the empty compressors, just to protect. So we are catching all the liquid that's coming back from the empty evaporators, and that's not a lot, and I'll come back to that in a second. Once this receiver or accumulator starts filling up, the ejector that's on the top left, that is sucking in or sucking out that liquid from that accumulator into this middle port on the ejector. So basically the ejector is there to make sure this accumulator doesn't fill up too much. That's the whole part. And once we are able to run with a lower superheat on our evaporators, the empty evaporators, that means the empty compressors can run at a higher suction pressure. But there's a whole system behind it, right? And for this system to run properly, that's where all the whole system comes in. So what do we need? We need the liquid ejector. We need the Danfoss case controllers controlling the evaporators. We need to have our pack controller that we mentioned before, and we need our system manager, the front end, which is basically the manager of the whole system. All those parts need to work in unison in order to make this work. Because the empty evaporators, they can basically run in two modes, right? This case controller, as you can see here, the AKCC55, it can run in, let's say, normal superheat mode, and I'll explain how that works in a second, or it can run in this low superheat mode. So it can toggle between the two. And this is, when it toggles, that's being decided by the system manager. Because on this accumulator here, we have a level switch. And basically the level switch, it's located at, let's say, 1/3 from the bottom. So more or less where this green part stops, that's where we have a level switch. And as soon as your liquid level is below 1/3 of this accumulator, we can run with a low superheat, right? The receiver it's filling up, but also again it's being drained out by this liquid ejector. Once for some reason the liquid ejector is not able to suck out all that liquid and the level rises in the accumulator, that's when this level switch is toggled, and that sends a signal to the pack controller. That's an input. That's just a hardwired input. But that input is being picked up by the system manager. The system manager says, hey, we have a problem on our receiver where the liquid level is too high, and it sends a signal to all case controllers, basically switching them back from this low superheat mode, what we call the ALC mode, back to normal superheat control, what we call the MSS control.
Which makes sense.
And that drains the receiver.
Yeah, which makes sense, because if you don't have something to tell it, well, we're flooding too much, we're sending too much liquid to there, you're risking those compressors. So then I'll just go back to the regular 6K or 10 degree superheat or whatever it's set up for on the fix. I guess that would be the fix mode, right? It would go back to all systems or all cases.
Sorry, yeah, correct. Yeah, that's when you go back to normal control.
Yeah.
And if we go back to normal control, let's say the normal superheat control, that's when we are running with 100% dry gas on the suction. So that means no liquid is going into this accumulator. So the accumulator can drain. And once it reaches a certain point again, that's when the system manager switches back to this ALC. So we can talk about this for hours, but this is just the lowdown on the system. And
okay. Yep.
I can explain a little bit on this superheat control, so it makes a little bit more sense, if that's okay.
Yeah, please do.
So if you look at this picture here, if we just see the evaporator just as a pipe, one straight pipe from left to right, where we have, let's say, full liquid going in on the left, and we have 100% dry gas on the right. Since about 35 to 40 years, the Danfoss superheat system is what we call MSS control, minimum stable superheat. We ran on the point you see here on the right. So basically, a lot of people seem to think that once you have, let's say, between dry gas and liquid, there's nothing in between, right? So you go from liquid to dry gas, or if you now have dry gas and sometimes sunny liquid comes out. But that's not the case, right? Between having dry gas and liquid, there is a phase in between. And that's the phase you see here on the right. So you have a phase where you have little droplets of liquid. And those droplets, those are being noticed by our system. So we have a temperature sensor on that pipe. And when we have these droplets passing the sensor, that's when the controller knows, hey, now I've went from absolutely dry gas to these small little droplets. And it knows exactly that this basically is as far as I can go with regards to superheat. And that's how we ran evaporators for a long, long time, running on this MSS point. And that's more or less the most you can get out of your evaporator and still have dry gas coming out of your evaporator. And that means you have a superheat probably somewhere between 5 or 10K or something, somewhere along those lines, which means you have a relatively low suction pressure on your compressor. But if we want to remove the superheat, we need to take it one step back. And that means we try to control a little bit more to the left. So basically, where this mist more or less starts, where these little droplets of liquid starts, but the full liquid is gone, that's where we are now controlling. And that's what we call the ALC point. So that you can see here in the picture, right of the middle. So basically where the liquid is gone and this phase of little droplets begins, that's where we are now controlling. And that's basically on the border. So that means for the evaporators that have a low load, so are not loaded very high, they will still have a completely dry suction line. But the controllers that are running on higher load and really have trouble becoming on set points, so to say, there we need to put in more liquid. So that means that those evaporators, those are the ones where we have some liquid coming out. And it's not huge amounts. Mm-hmm. The experiments the data we have so far is that more or less 30% of your empty evaporators will have some liquid coming out, and it's around 5 to 10%. So if, let's say, we take the highest of that, let's say 10%, that's still around 3% of the total liquid we have coming back. So it's not a lot, but it's enough to wreak havoc on your compressors if needed. So that's why we need this accumulator.
Yeah, so you said that this now is monitored by a temperature probe. Is it still the same temperature probe used when you use when you're not using adaptive this ALC point? So like, I mean, at the outlet of the evaporator, a temperature probe and the pressure probe, because you need that. Is there an extra probe as well, or you're just using that standard temperature probe that you were always using in your case controllers?
It's the same one. We have been using AKS 11, which is a PT1000 sensor, for about as long as I can remember, which is probably around 35 years or so. It's the same one, and you need to place it on the suction line, of course, in the right position. But it's the same sensor. If you're running MSS or ALC control, same sensor, same location.
Okay, perfect. So now with this, I should ask you, how many systems globally do you have using this solution at this point?
The liquid ejector, that's quite new. Let's say the HP ejector, the one that we have thousands of systems running.
Yeah, I've heard lots of those.
Yeah, I think liquid ejector, we're into the several hundreds.
Okay, so there are 100. That's cool. You got a couple hundred out there, so that's great. Have you ever came across any situation, because now you got a kind of a flooded evaporator, semi-flooded evaporator, because you're running real low superheat. You know, you said you got some percentage of liquid droplets. What happens when you have a frozen up coil now, or you have fan motors not running because you got to boil that stuff off? Usually, does it run into a bigger issue because now you're using your system manager to control? Okay, I got too much liquid. Let's turn everything else off. You know what I mean? Turn everything back to normal superheat mode. But you have one system that is a frozen coil, or the fans are out, for an example. Now you wouldn't be running that. What have you came across any experiences on how that works if you run into those situations?
Yeah, that can happen, of course. And first of all, I'm not allowed to call it a flooded system
Yeah.
because that
Okay. Yeah.
is
Good.
that resembles, let's say, an industrial system too much. And I have a colleague that gets really upset when I call it a flooded system. So,
Okay.
but no, just all jokes aside. But yeah, that can happen. And what we do on the pack controller, this system manager, that we have a system called PO optimization, which houses in the pack controller, but is being controlled by the system manager. So basically, the system manager, it keeps track of all cases that are connected to it. So let's say all empty cases, and it's really checks, are all cases still on getting their set points? Yes, then we can raise the suction pressure on the MT, because there's no need to run with a lower suction pressure if it's not needed. And also in that system manager, you can check which case is responsible for maybe not optimizing, right? So if there's one or two cases that for some reason do not reach their temperature, we cannot optimize the suction pressure. So we have to keep it lower because one of those two cases. And we can see that in the system manager. So we can see exactly in the system manager when we connect from remote that dairy cabinet in the corner, that's the one responsible for having a relatively low suction pressure. So that means something could be wrong. That could mean we have a broken fan. It could mean it's overstocked and there's no airflow. It could mean that it's frozen up. So it's time to check up. So we see that data in the system manager from remote, and then you can go on site to see what's wrong with that particular case.
Yeah. Okay, good. So there's at no point where the system manager would say, okay, these two cases will go back into fix mode and the rest stays in optimize mode?
No, basically it's all or nothing. So we switch the whole MT to MSS or ALC as a whole, not one by one. So it's the whole suction group, so to say.
Makes sense. Yeah, totally.
So this is, like I said, this is basically the change we had from MSS to ALC control. And like I said, the MSS, that's what we've done for about 35 years with the AKV valves. And I can maybe really short show you how that really works. Because we have had quite a lot of questions on how does the controller find its optimal superheat. And it all has to do with this MSS line, right? We have an MSS line, what we call the minimum stable superheat line, in each evaporator, be it an evaporator or shell and tube heat exchanger or a plate heat exchanger, everything that is evaporator has what we call an MSS line. So that means right of that line, you run into dry conditions, left you are in the unstable part. And how the controller works, basically when the controller is brand new out of the box, it will start controlling with a relatively safe superheat. And as you can see here, the red line, it starts around 12K superheat, so a relatively safe superheat. So we open up the valve, we start measuring a superheat. So we have a pressure, we have a temperature that gives us a superheat. And as soon as the controller sees that the superheat that it measures is stable and it's not going up and down, it's not spiking, then the controller starts to lower the superheat reference. And the reference, that's the red line you see on the screen here. So basically, it starts opening up the valve more in order to get the superheat down. And as soon as the measured superheat, which is the blue line, is still stable, we can continue lowering the superheat reference. And at some point, we will hit this, what we call MSS line. So that means we got as much out of the evaporator as we can, and we cannot go higher. So that means we start seeing these droplets coming out of the evaporator. And that means we have an evaporator suddenly that starts hunting, because we have little droplets coming out. So we have that sensor, which is on the suction line. It becomes cold and warm and cold and warm because of droplets passing by. And that's when you see this behavior, as you see here with the blue line, the superheat going up and down and up and down. So that's the point where the controller knows, okay, now we are in this, let's say, mist phase of little droplets. And now I should back off, basically, because if I go on, we will start to see some liquid.
Yeah.
So that's when the controller raises the superheat again. So you see the superheat reference going up, the red line. But you know, the controller is just like any standard refrigeration engineer. It's extremely stubborn, and it wants to get that superheat down. So after some time, you know, it's true, right?
I love it. I love it. It is. I was.
Oh, yeah, it was very stubborn. At some point, it will try to get that superheat reference down again. And this is a cycle that basically repeats 24/7. Hitting that mist phase every single time, backing off and trying again. And that's how we run on, let's say, the lowest superheat possible all the time.
Okay, so that's the algorithm built in, which I like that you pointed that out, because I've troubleshooted and I supported lots of different controllers, and I've seen lots of times where a technician or a manufacturer was setting it up and tried to set super low superheat, but every time I get down there, it goes down just nice and smoothly like your red line there, but you just, all of a sudden, you're all over the place. So the valve's opening, it's closing, it's opening and closing. You get a lot of hunting. So I'd always say, raise up your superheat. And they start to raise it up and it's like, oh, it's stable again. So you're doing this, the algorithm is just doing that in the controller, so you don't have to fine tune it as much. I do have a question though, because I've seen this lots of times where, and I didn't know this until I started working with coil manufacturers, that coils, plates are designed for a specific superheat. So you need to know that with this controller, because like when you look into a manual on a case, they'll say it's recommended, the best efficiency for this case would be, say, 10K, we'll say 18 degree superheat, or 6K, 10 degree superheat, doesn't matter. And when you go lower in that the superheat could potentially be low. Will this take that into account? Do you need to know exactly the design superheat for that plate or that coil, or have you ever heard of that before?
Yeah, I have heard about it, but we don't take it into account, because in the end, the controller doesn't know what's on the other side of that cable, so to say, right? Mm-hmm. It's just, it only knows there's a valve and there we need to measure a superheat. So what we do out of the box, there is a minimum and a maximum superheat set in the controller. And by default, it's minimum 3K superheat, maximum 12. That tends to confuse some people, because they think 3 and 12, why the hell 12? I don't want 12K superheat in my controller, but it's basically setting some borders. So that means that your optimum superheat can be somewhere between 3 and 12, and you just let it run. And with this algorithm that I just explained, it will find the lowest superheat, because that's always the end game. The controller is always trying to find the lowest superheat possible. And if it's 3, it'll go to 3. If it's 12, it'll be 12 or 8 or 7, whatever. But it will always go as low as possible. And we have seen customers saying, hey, I don't want 12. So they push down the maximum superheat, the 12 to 6, because they say, I need to have 6. But that can also cause trouble, because sometimes this evaporator cannot handle superheat of 6. It's right. Only stable at 8. So when you're then pushing it down to 6, you can push it basically into all kinds of problems. So keep those two values, default 3 and 12, and it will always go to the lowest superheat possible, basically.
Yeah, so this is what I talk to so many people. This is different. This is not a TX valve, a TEV. It's different, you know, and you're always watching, trying to maintain. And even in a TEV, the superheat's all over the place, especially when you get different pressures. But we got to kind of reprogram ourselves. We're not always looking for a flat line, because conditions change. So you want to run the lowest, but there's sometimes it might be running at 10 degrees and superheat, and then maybe it's running at 4 degrees superheat. But in this controller, it's trying to maintain the best. So it's something that you need to wrap your head around, that it's not always going to be that one fixed flat line, because especially in a supermarket application, there's so many dynamic CO2, so everything's changing. You do want the lowest superheat at all times if you can, but with conditions changing, it's going to have to change as well.
Yeah, absolutely. And coming back to this liquid ejector, just to wrap that up, here you see a picture where we have this CALM system, or ALC control, working and not working. And you see here on the right part of the system, you can see where this ALC is off. So that's where we are running in normal MSS mode, so completely dry suction. And you can see that we have a suction pressure of around -6. As soon as we enable this ALC control, so we enable this CALM system, that's when we see improvement, and suddenly we are running at -3 on the MT compressors instead of -6, simply because we are removing that superheat from the MT evaporators.
Yeah, and that's perfect. Now, once again, higher suction, more capacity, less power, a lower compression ratio, I guess. And it's I like that. I like that. But this, once again, is all built in. It's a full system, right? So you need all the different parts. Can you use this LE ejector with other manufacturers' controls? I'm guessing you wouldn't get the full benefit of the system, though.
Yeah, that's correct. In the end, the ejector, it has 2 solenoids, and whether you control it from a Danfoss controller or any other brand of controller, you simply have to activate the solenoids. You can do that from any controller or PLC system if you will. But if you want to have the benefit of the full system, that means that you need to have the Danfoss case controller, pack controller, system manager. You need to have the full system to get the absolute most out of it, as you can see on this picture here. And again, ejectors, it sounds like a magic word, and it really isn't. You really need to stay focused. You need to really make sure it really makes sense. Because even if you have a liquid ejector, it doesn't make sense always. Because like we said, the point is to raise the suction pressure on the empty compressors. But if you have a booster system, if you have a higher MT suction, that also means you have a higher LT discharge, right? Because the LT compressors, they have the discharge going into the MT suction. So we can, if you are, let's say, have a system where you have the ratio between the LT and the empty part is just as much. So we basically have, it's 50-50, more or less. In that case, it doesn't make sense, because whatever you're saving on the MT compressors, you're losing on the LT compressors. So only when you have, let's say, a ratio of 70-30 MT to LT evaporators, that's where it makes sense, because you're saving, let's say, 70% and you're losing, let's say, 30%. And then still you're gaining quite a lot. But and we also had some tough lessons there. I can show you a picture. This was the very first liquid ejector system that we set up, and you can see the suction accumulator all the way on the right in the red circle. And basically, it is just as big as that red circle, more or less. And this was the very first system that we tested a liquid ejector on, and the results were not great. Because in this system here, the ratio between empty and LT evaporators was equal size. So everything we gained on the empty, we lost again on the LT. So it was basically zero gain at that point. But still, it was very valuable knowledge to learn.
Yeah.
So
thank you for sharing that, right? Thank you for opening it up and talking about it, because that's important. Because if you have 50-50, it's not going to benefit. I like that.
No, correct. And then, yeah, also here we had quite a large suction accumulator because we didn't really know how much liquid would really come back. So we played it safe. And I can show you a very short video of this. This is a side glass that is on the bottom. So this 1/3 of this suction accumulator, and you can really see that now, because now it's full. So now the ejector starts doing its work, and you can see once it starts removing the liquid from that accumulator, you can see the level going down quite rapidly. And this is a relatively big vessel, and still you can see the level go down quite fast. So this ejector, it's really working, as you can see.
Yeah, because it's taking that liquid now, putting it back into the receiver, the flash tank receiver.
Correct. Yeah. Yeah, and only to have, let's say, more efficiency on the empty compressors.
Yeah. That is neat. So there's a few hundred of these out there. Learning lessons. Do not do a 50-50. 70% medium, 30% low temp. I like it. Anything else that you found along the way? Because I'm sure there was trials and errors. So that was probably the biggest one. So I would assume now you would have smaller suction accumulators in that one because it empties really quickly, as well as in this with this system. Would it be able to have smaller compressors now, or like less compressors on a rack if you did it this way? Because now you got a higher suction. Is there any benefits in that sense?
Yeah, that's something that comes along. So with the whole ejector platform, like the whole point again is optimizing the MT compressors. So when we have, especially for the LP and HP, where we are, let's say, taking away suction gas from the empty pack, that means that you maybe can run on 2 compressors instead of 3, or 3 smaller ones where normally you would have 3 bigger ones. That could be an option. And with the liquid ejector, yeah, of course, you could possibly remove a compressor, but the main point is raising the suction pressure. That is the main point in the end.
Yeah, and that's always how it's been in refrigeration. It's not new for CO2. You always want to have the highest suction as possible to maintain your refrigeration temps. Refrigeration 101. That hasn't changed.
Yeah, there you go. Yeah.
Oh, I love it. So, anything else you would like to add, Patrick?
Well, I think hopefully now it's pretty clear the flavors of ejectors we have. So in the end, it is just 3. And please make sure and remember that an ejector, it's not a miracle cure, right? It doesn't solve any system. It doesn't solve any problem. You really need to pay attention when to use it, when not to use it, and when it makes sense. And if you don't know, if you need any help, reach out to me or to your local Danfoss supplier, and they can help you out. And that's the last slide. Probably I wanna share because we have quite an extensive training platform. We have done a lot of trainings on CO2, and you probably have seen this website and page before, Trevor. Yeah. We have done a lot of trainings last year, and all of those are now available as recordings. So I'll share this link with you. You can share it again in the description, and people can navigate to this and have a look at all these trainings. It goes from very basic introduction to CO2 into transcritical ejector systems, fully advanced. So there's something for everybody there.
Yeah, no, and I love it. So I'm going to have this in the description. You're going to want to check this stuff out because this is really important. You want to continue to learn. You want to continue to grow your CO2 knowledge. You got to spend the time doing it. You got to invest the time because it's already here. You're going to see more and more systems with CO2, and it's just healthy for you to continue to learn refrigeration. I love it. Patrick, I want to thank you so much for taking the time. I want to thank everyone for taking the time to listen. Please comment. Send your reviews on the podcast. We really appreciate this. This is how we continue to grow, get awesome guests like Patrick on here. Patrick, thank you so much for taking the time today.
You're welcome, Trevor. And everybody is more than welcome to connect to me on LinkedIn. Please find me and I can help out wherever I need.
Awesome. Thank you so much, Patrick. Thank you, everyone. And we'll see you at the next CO2 Monday.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.